all the people on sugar highs. Welcome everybody to the department colloquium. It's my pleasant duty to tell you a few words about our speaker.
Can't hear you.
You can't hear me? Really?
Yes. Just speak a little louder.
I was told that there are built-in microphones. Okay, speak louder. All right. Hey, David, is that true that you can't hear me? No, okay. Okay, Richard got his BS from Caltech and then his MS and PhD from Berkeley in 88 and 91. And while he was here, he got the Jury Award, which some of you may know about, is an award for system science, outstanding research in system theory. He returned to Caltech in 1991 as a member of the mechanical engineering faculty and was a co-founder of a program called Control and Dynamical Systems, abbreviated CDS. And then he was pretty active in some Air Force programs aimed at really trying to take control theory and moving it into practice for all kinds of things, especially the control of jet engines. And I think as a consequence of this, or perhaps during the course of his travels there, he decided to take a sabbatical in 1988-89 as the director of mechatronic systems at the United Technology Research Center, UTRC, where he managed a group of engineers who were engaged in active control, sensing technology, and modeling of complex systems like these jet engines, which were prone to stall and flutter and all of those kinds of things. I was in DARPA in those days, and I remember they had this wonderful program called Pictures to Code, which was really a way that United Technologies had of going from complex models to embedded code for these wonderful Pratt & Whitney jet engines, which are still a staple of our fleet, commercial and military. Okay, so right after he came back from his sabbatical, Caltech made sure that he put in his dues, and he was appointed as the chair of the Division of Engineering and Applied Sciences. The word chair at Caltech actually is a misnomer for dean. So he was the dean of engineering from 2000 to 2005, exactly 5 years, and. That was the division was about 100 faculty, 400 undergraduates, and 500 grad students. Caltech, of course, is the largest unit in Caltech, so I think he flourished in this role. But 2005, 5 years later, he came back and to research, and he got especially interested in synthetic biology and the large set of partnerships including sort of competitions. He ran some competitions in synthetic biology, one called iGEM, and then he was on the. He also helped start a new initiative at Caltech, or IS&T, for Information Science and Technology, and managed to continue to do his research till 2020, when Caltech descended on him again, and this time to become the Dean of Biology. It's called the chair of the Division of Biology and Biological Engineering. And actually, I was preparing to do this little introduction. I went and looked him up, and I think I can't tell if it's Wikipedia or something like this, and they called you, Richard, world famous biologist. You've got nothing to do with engineering anymore. But mercifully, he's still a member of the IEEEs and ASMEs and all of those things, and he's a member of the National Academy of Engineering, fellow of the IEEE member. His awards include the Bodie Lecture Prize in 2016, the Control Systems Award in 2017, and the Ragazzini Medal in 2019. He has written 3 books. First one, which we still use amazingly in our robotics class. Feedback Systems, an introduction to for scientists and engineers, which Ben was just plugging a few minutes ago, and Biomolecular Feedback Systems, all excellent books, especially the latter two. So he's supervised or co-supervised 70 students and 30 postdocs. And he's on numerous advisory committees. I won't read them all out to you, but I can tell you that I was at the Royal Institute of Technology, Stockholm, last week. And then they said, boy, we are fortunate because Richard Murray has been on our advisory board for a center called WASP, which stands for the Wallenberg Institute for something. The Wallenberg AI, Autonomous Systems and Software, actually with Claire. But what they said was, boy, we're so glad we asked him to stay on, and he's been on the advisory board for the last 11 years. So I think the people are endlessly thrilled to have him. Let me also tell you that most recently, he, along with Eric Schmidt, have been chairing a new advisory board. I think it's called the Defense Innovation Board. There was one called the Defense Innovation Board 2016 to 2020, but now there's a new board, which really is transformative science and technology, which was established in 2023. And they've been very instrumental in really thinking a little bit behind the scenes, off the press, about really how we should think about AI and emerging technology. So anyhow, this is, I know, a slightly wrong introduction, but this is really one of our most eminent alumni, and we are all super thrilled to have him here. And without further ado, I'll present your department chair, Claire Tomlin, to present him with the special award that she'll tell you about.
Sorry, Richard, we're really cutting into your talk. So each year we have a really nice thing we do, which is our faculty in EECS. We have a committee, and we nominate. There's a lot of people that get nominated for our Distinguished Alumni Award, and we have a committee that goes through all of these and has the pleasant duty of choosing who is going to win one of these awards. And for the 2023-24 year, it's our pleasure to announce that Richard Murray won the Distinguished Alumni Award in EECS. I get to present Richard with this award. We had the ceremony back in May. But, you know, this is one of those things where we kind of figure out, it all gets, you know, announced in April, and then, you know, by May, and then we're like, Richard, can you come? And he's like, no, I've got a qualifying exam that day. So, in fact, we're presenting it. So this is our kind of ulterior motive. We're really happy you're here giving this talk, but we're also happy that you could come and receive your Distinguished Alumni Award.
Well, thank you very much.
Thank you, Richard.
Well, thank you, Claire and Shankar, for both the introduction and the award. It's certainly an honor to receive the award. So I wanted to talk today. I kind of tried to put a provocative title. I think it worked, at least in terms of what people have said about kind of autonomous systems and some of the work we've done in that side. As Shankar mentioned, we've also done a lot of work in synthetic biology, but I won't talk about that today. But I maybe wanted to start a little bit, partly due to this award, with reminiscing just a little bit, one slide's worth, about my time at Berkeley. So I was a graduate student here with Shankar starting in 1985 and finished in either 1990 or 91, depending a little on how you sort of count these things. But I sort of look back and, this was a very formative time for me. I mean, it really, sort of shaped things. And so, there were a lot of pieces of that. Here's one piece of that. So you may or may not recognize me. I'm the guy on the left, and Chris, he's the guy in front over on the right. This is one of the robots that we built that was part of my thesis that was called Styx. This was a multi-fingered hand because it had two fingers. That's multi, right? And so this was sort of where the state of the art was. I think this was in 333 Corey Hall probably, or something like that, up on that third floor where the robotics lab is, and still is. I was just there today. Yeah, right. The lab probably looks about the same, yeah. The department should fix that, Claire, I think. So anyway, as I said, at the time, right, we were sort of working on flexible end effectors and grasping. This became part of the robotics book, which was on robotic manipulation. But these experiments, sort of interesting. You kind of remember some of these things. I did, work in these kind of robotic hands. This was a robot called Acrobot. It was built by John Hauser and I. It was supremely dangerous. These are basically big pieces of metal with big motors that spin it around, right? But you can see we've got a safety gate there made out of PVC just to make sure, right, that these heavy chunks of metal don't hurt anybody. And so I remember Acrobot is something that we worked on. And this I got an email about 2 weeks ago saying, oh, could I have the model for Acrobot that you used in this paper? I'm going, dude, this is like 33 years ago or 35 years ago. I don't have the model anymore. Anyway, I did look. I didn't have the model anymore. Another one, which I don't remember, Chris may remember, this is like Robot World or something. Was that the name of this thing? We got from HP. So this is the HP auditorium, right? So there's a kind of connection. I remember spending lots of time on this, breaking it, and Ruthann, my wife, will tell you that I would then stay until 1 a.m. to fix it and get it working again because I didn't want to tell Shankar that I'd broken the Robot World thing, but we were trying to interface it and other things. The other ones actually made it into papers. This one we never wrote a paper on. I got my most scathing review when I tried to write a paper on peg and hole insertion and basically got told by the reviewers this was the most ridiculous paper, kind of overkill on the experimental end to do something simple. And so this paper got completely trashed. So that was sort of the end of anything going on there. So these are some of the things that I remember. I also met my wife, Ruthann, here. You may recognize that's Corey Hall in the background. This was a picture taken by my grandmother when she visited. So I look more or less the same. You can see that in whatever time from me and Chris, I started wearing glasses. So that was another thing that Berkeley did to me, was that it sort of caused me to wear glasses, probably squinting too much at the wiring diagrams for Robot World. So anyway, so it was a really formative time, and I remember lots about it. Another event, that occurred while I was a graduate student, that was, one that I think, was very important to me, was that Shankar spent some time in India. He was on sabbatical. It was my most productive time ever as a graduate student when Shankar was not here. I remember that. I remember you had this big computer that you would lug around, right? That was like this suitcase-sized computer so that you could actually dial in on a modem at 300 baud from India, right, to send email to the graduate students, which were always very short because if they were too long, the connection broke. And so, sort of didn't work. So I remember that. But we got to go visit India. And so this is Shankar with his parents at his parents' house in Bangalore. And so we had a very pleasant visit there. This is actually Ashu Rege, who I actually met again, who was the VP for software at Zoox for a while. And so I got to see Ashu not that long ago. Pardon?
He works for DoorDash.
It works for DoorDash now, and so I put up some embarrassing pictures of Ashu when I was speaking at Zoox. This was Shankar's parents' house. And you probably can't see it here, so I sort of blew it up. This house had a name. It was called Silicon Valley. And so you could tell that Shankar's family was very proud of Shankar and where he was and where he came out and sort of all of these things. And so this is kind of some of the things I remember from my time here. And again, it played a very influential role in me and the way I think about things and sort of what I did afterwards. I put one last picture. I was sort of embarrassed because I sort of had 3 robots up here and instead of people. And so I put one last picture. This is one that I took just 3 weeks ago. Shankar mentioned that he was in Stockholm. I was too. But I stopped by in Lund, Sweden. And so this is me on the left, obviously, Ruthann on the right. The guy next to Ruthann is Carl Ostrom. So Carl is my co-author on the Feedback Systems book. I met Carl here at Berkeley. And so really that was where that collaboration started. And Carl has been a lifelong friend and colleague ever since then. And so Carl is 90. He just turned 90. And so we went and had dinner together. The person next to him on his right, our left as we're looking at it, is Kalle Ostrom, his son, who's also a professor in machine vision and machine learning at Lund University. And the person next to him is Oscar Ostrom, Carl's grandson, who is a graduate student at Lund University, but spent a summer at Caltech working with Pietro Perona, who was Jitendra Malik's graduate student and shared the lab. We graduated at basically the same time. And so it just shows the kind of connections that happen. And one of the things I love about sort of being in a university and being an academic is this sort of network of people that you meet and that you have for a lifelong kind of career. So all of you who are graduate students and postdocs and other things, they're saying, I don't want to be a graduate student. I look at what my advisor does and I don't want to spend my time doing that. I can tell you it's a wonderful career and it has a lifelong benefit to it, and I encourage you all to think about it as one of many possibilities. So anyway, so that's a little bit about what I remember in my time at sort of Berkeley. Okay, so With that, maybe I'll talk about the things that I've done since then and most recently. And so I want to talk a little bit about some of the work we've been doing in autonomous systems, and in particular, this is work of two of my graduate students who both just defended their PhD in the last 3 months or so. Purva Bhattachala, who's now a postdoc at Princeton, presidential postdoc at Princeton, and Josephine Graebner, who's doing some work with JPL. And so this is motivated by thinking about autonomous systems, but really thinking about safety critical systems, right? When is it that a system really needs to be safe that you can bet your life on? And there are a lot of safety critical systems that are out there. Certainly one we can think about is aircraft, right? So, I flew up here, and so pretty much felt like I'd get here, right? We all fly in planes, these we think are extremely safe. And I think it's a good question to ask, well, how are they safe? What do we do as engineers? What do we do as an engineering discipline to make sure that, we're willing to build these systems and put people's lives at risk and put them on them? And of course, if something goes wrong on an aircraft at 30,000 feet, right? You better, have a plan in terms of, how you've engineered the system not to do that. Increasingly, of course, we see, self-driving cars, and of course, in the Bay Area, we see these quite often. This is one by a company in autonomy that no longer exists under that name. The company is now called Motional. I put it up in part because a member of the kind of controls community, Emilio Frazzoli, was one of the co-founders of this company. And one of my PhD students was sort of the first full-time engineer there, a guy named Eric Wolf, who now works for Cruise, as it happens. But it's sort of, one piece of that industry. But there are lots of other safety critical control systems. The electric power grid is increasingly safety critical, right? It can't go down for too long, right? Things depend on it, right? And so how do we make these really safe systems? And as we start making autonomous systems, in particular that middle picture, how are we going to do that? So what I want to talk to you about today a little bit is just kind of the motivation and setting for safety critical systems and how we certify safety critical systems. I'll focus on kind of autonomous vehicles as the central point for that. And then I'll talk about some of the work we're actually doing in that area. So this talk is kind of half about what should we as an engineering community be thinking about in terms of hard research problems, hard practical problems to solve, and then a little bit about what are we doing at Caltech that's aimed at some of that and some of the open problems associated with that. Okay, so I spent a lot of time and actually worked with, Edward Lee and Sanjit Sesha and Alberto Sangiovanni-Vincentelli and others, Claire and Shankar, thinking about the design of these systems. And so when we look at kind of a modern network control system, if you, open the hood or open the trunk probably of a self-driving car, what you're going to see is some sort of an architecture like this in terms of what's controlling it, right? So you're going to see there's a physical system with sensors and actuators. There's a low-level kind of control loop. There's some sort of trajectory optimization, receding horizon control, things like that. High-level decision-making. Do I stop? Do I go? Do I turn left? Do I, kind of go into some safety critical thing? And increasingly, these are very networked systems, and so we might have lots of different controllers running, lots of different optimization algorithms running, all running on slightly different clocks. And I was talking to Edward a little bit about, how do we keep track of clocks in these distributed systems, for example? These are now connected to cloud resources, right? So, you'll have a bunch of cloud resources that are part of that. And so I think that these systems are really interesting. They are the way that we design the power grid. They are the way that we design self-driving cars, increasingly aircraft and other things. And they're just enormously complex, right, as we do these. And one of the things that we find of sort of drawing these sort of vertical or horizontal blue lines is that we tend to separate these into different layers of abstraction, right? So you have the lower layer and this kind of trajectory optimization layer and this upper layer. And we do that because that's the way that we're able, as an engineering community, to get 1,000 people to work on a project, right, and sort of have it all come together. You can't have all 1,000 get around a conference table and talk about things. We need to separate it out. You guys worry about this, you worry about this, you worry about this. But in fact, that often is where we see a lot of the errors, right, is across those layers of abstraction, right, because somebody assumed something that, somebody else didn't know they were assuming, and so something goes wrong. So I think as we think about these systems, it's interesting to think about, how do we keep track of that? How do we manage that complexity? How do we wrangle that complexity? And there are two types of areas. We can think about, sort of horizontal complexity. At a given layer, we may have many algorithms running that are doing the same things, and how do we connect those together? But we can also think about, kind of vertical layers of complexity as we do these. And so there are lots of examples I've already said, aerospace systems, autonomous systems, factory automation, smart buildings, smart grid, they're all increasingly, these are the types of architectures you'll see. And so I think we need to understand these architectures. And there are lots of interesting design challenges, right? How do we define the layers and the interfaces, right? What should those be? Why should they be that? How do we think about these kind of vertical contracts between the layers, but also these horizontal contracts between multiple devices that are running all at the same layer of abstraction? How do we scale this to many devices, right? And so as we start thinking about 300 cars driving around, maybe talking to each other, right? How do we do that? What if it's 3 million cars that are driving around, right? Or nodes on the internet, or all of these things. So I think those are interesting. And of course, how do we think about safety, robustness, security, and privacy for these complex systems? This is getting worse instead of better in terms of the challenges as we start putting in optimization all over the place, right? Because we can now do real-time optimization and sort of throw those things in. And then, of course, machine learning is coming in all over the place as well. And so I think an interesting question is just, how do we not design these systems? That's interesting too, but how do we actually make sure they're okay, right? So how do we verify and validate these systems? And we can argue, and I will in a second, that we build complex systems, we build the power grid, we build aircraft, we get it to work. I think a question is that going to keep working, right, as we increase the complexity of these systems? And what should we be doing about it? Okay, so let's look at these kind of safety critical autonomous systems. And I think one question we can ask is, well, what do we mean by safe, right? How safe do they have to be? So we can look at some statistics. In the United States, there are about 7 deaths for every billion miles driven. So I titled the talk 1 in a billion, right? Because this billion comes up all over the place, right? And 7 deaths in every billion miles, right, means they're pretty rare events, right, really, right? Probably none of us in the room have been in a car that killed somebody, right? That's pretty unlikely. Maybe you know somebody who got killed, right, in a car accident. You probably know somebody who's had a collision. You've probably been in a collision, right? But killing somebody is really a rare kind of event. So one thing we could say for the autonomous vehicle industry is we'd like to be as safe as human-driven cars, right? Maybe that's a good metric to use. So sort of argue to you, I think that's not good enough. And I'll argue it not on a technical level, but on a society level. So 7 deaths per every billion miles driven turns out to be 35,000 deaths, actually about 40,000 deaths per year in the United States, right, due to car accidents, right, where a human dies because something happened in a car. Car ran into a person, another car ran into a car, right, but a car was involved in it. And so if you've got 35,000 deaths per year, if you had 1% penetration of self-driving cars, and I would argue to you that in San Francisco, you're getting close to that maybe, right? I'll show you a video in a second. But, if you think about electric cars, right, like the first electric car I drove in was Chris's Tesla at about 70 miles an hour on a street just over a little bit here. No, it wasn't 70. It must have been 35. I'm sure it was only 35. Anyway, but, now they're all over the place, right? And you still owe your okay, so good. So, we probably got 10%, maybe even 20% in the Bay Area penetration in about, it's probably 15 years or something like that, right? So 1% is not an unreasonable number to think about. In the next 5 years, 10 years, we might have 1% self-driving cars. So what would that mean, right? At 35,000 deaths per year, if 1 out of every 100 cars, right, was an autonomous car, that means 350 deaths per year, right, from self-driving cars. That means every day there's an article in the San Francisco Chronicle, right, saying, UC Berkeley professor gets killed, right, walking across, right, to Soda Hall to attend a lecture, right? Person in Florida gets killed, right? Every day, right, a self-driving car would kill somebody. And I think people would say, you can't do that. That's, these things are dangerous. They're killing people, right? We need to stop. So I think that 7 deaths per billion miles, as safe as humans, isn't good enough. To err is human, right? But we're not going to allow computers, right, that sort of same luxury. And we see that in medical professions and other things as well. When you get medical robots, right, they have to be better. So I think they got to be better. So one question we can say is, well, how much better can we get? Maybe this is the fundamental limit, right? We just can't get any better. So let's look at other modes of transportation. So trains and buses, public transportation, turns out, on order, right, not quite 10, a little bit, sort of off from that, but, 0.1 to 0.4 deaths per billion miles, right? So really quite a lot safer, right, to do that, 15 times safer, right, I took Bart over from San Francisco this morning, right? So that was, safer than me driving, right? If I'd rented a zip car and driven over, that would have been more dangerous, right, by about a factor of 15.
If I drive into a tram, it kills me, where you count it?
Yeah, I mean, it's if the tram was involved, right? Yeah, that's a good question. Maybe it counts both. I don't know, right? So now, of course, these are on tracks, right? There's really only one thing you have to control, which is the speed, right? I mean, there's lots of reasons that it might be safer, right? It's much more structured for trains, right? Buses a little bit more. They're also very big. We probably stay out of their way, right? All of those things. Okay, so, but really, kind of, I think the safest transportation mode is aircraft, which is a little bit surprising, right, given, you're flying at 30,000 feet. But it turns out it's 100 times safer, right, to fly a mile than to drive a mile. So I came up from Pasadena yesterday. Definitely I should not have driven, right? It was 100 times safer for me to take Southwest, right, which is what I did, and fly up here. So 0.07 deaths per billion miles flown. Right? Really quite. And you think about it, when an airplane crashes, a lot of people die, right? So hundreds of people die at once, right? And so you think about like the 737 MAX and other things that happened now a couple of years ago.
Just a quick question on that. So that statistics from 2013?
Yeah, the paper was from 2013. I don't know what it is today.
Probably lower now then.
Could be, right? Although if you look, I did a little bit of checking at one point. If you look at sort of deaths around the world, et cetera, it was, for planes anyway, it was about that, right? Because again, 737 MAX happens, but there's billions of miles flown, things like that. Yeah, so this is where that came from. Okay, so, I want to argue to you that, maybe 100 times safer than humans is where we ought to target. Can we get there, right? Maybe 10 times, I don't know, right? But I think it's safer than humans. And we got to think about how in the world are we going to do that? Okay, so how is it done in the aerospace industry, right? I'm going to argue to you, at least that's the safest in terms of transportation. So there's lots of sort of things that are done, right? So first off, there's strong requirements, right? They're basically DO-178C is a FAA requirement for flight critical software, right? So it's a set of things you have to go through to certify the software and say this software is safe enough for me to fly. So there are certification requirements. The way that DO-178C works is they have different software levels, right? If this software were to fail, what is the effect of that? It could be no effect. This is the entertainment system going out, right? Or it could be, people on the plane die, right? This is, the flight control computer crashes, right? And the thing crashes into the ground. The 737 MAX would be a, sort of level A failure. And then they basically do failures per flight hour, not mile, but flight hour. And so for level A software, all of the flight control software, et cetera, it's one failure every billion hours, right? Billion comes up again, a little bit randomly, but that's 10 to the 9. That's what you ought to be thinking about. And so how in the world are we going to do that? So 178C says, here's how this will be done. Here's the evidence you have to provide us, right, in order to do that. And so there are all sorts of things that go into that. And so you see, for example, that model-based development, right, simulations and other things can be part of that, right? Formal methods, analyzing things or so your code doesn't have any deadlocks, live locks, et cetera, can be part of that. Testing is a big part of that, and I'll sort of talk more about all of this. A big part of that is just the notion that we might use fault trees, right? And so we can say, what are the things that would cause an airplane to fall out of the sky, right? Well, you could lose an engine. Actually, they're designed so they can fly on one engine. So you have to lose 2 engines, right? So if you lose 2 engines, you still can coast down, right? So maybe you don't even need the 2 engines, right? So now you can say, well, what is the probability, right, that we lose all of the different things that might make it so we can't do it? And so you can put together a fault tree and say, well, if any one of these things fails, right, we would have a catastrophic failure. But for this one to fail, all 3 of these things would have to fail, right? And then you can just start doing some kind of simple probability, and you can say, well, for this subsystem, right, that subsystem maybe fails at a rate of 10 to the minus 8, right? Why? Because it's got 3 things at 10 to the minus 9, roughly speaking, right? We'll just kind of take factors of 10 on this stuff, right? That middle one at 10 to the minus 9 is because you've got 3 things at 10 to the minus 3, multiply them together, right? Not as long as they're independent and other things, right? So we go through that sort of analysis in an aerospace system, and this is really what they do. So Alberto and I and Edward spent a lot of time looking at electric power systems, and what they were doing was going through and saying, okay, well, this could fail, or this could fail, or this could fail, and here's the backup, here's the redundancy, here's all of this stuff. Let's go calculate out the probabilities, right, and make sure, because if the electric power system on an aircraft fails, the aircraft is going down, right? That's it. But for example, on an aircraft, there are 2 sets of circuit that go in every set of component, and there is a set of complicated networks that always will make sure that there is electrical power going into that backup circuit that will only power the things that are needed for the flight control system. So you could lose both engines, the power for the flight control system will stay up and running, right? And so they think about all of these things and how to do that. So I think, it's a good example of the types of things we might need to do, and people are doing. We use... So that's where they have to go show, right? The shorts are independent. One advantage there in terms of doing these is we have lots of fail. These things will fail once every 1,000 hours. And I can get lots of statistics on that because there's lots of aircraft flying, right? So I'll see stuff fail all the time. Most of the time when you take off, the engine, for example, will have 1 or 2 sensor failures in it, right? But it's designed to be redundant, so there's yet more redundancy you can do that. So we have lots of statistics and we can check that independence assumption, right? So that's one of the ways we do things there. So a lot of it is not sort of a formal proof or whatever, but a lot of just statistics about these things happening. So, but yes, you got to make sure they're independent. So we can do model-based design, software in the loop, hardware in the loop testing, all of these things. Those are all done. One thing is you have to think about fleet-wide analysis, right? So you got to think about the fact that there are going to be 1 million cars out there and they're driving lots of miles, right? And so every corner case that you can imagine seeing, you're going to see, right? And so you have to think about what are those corner cases? How often am I going to get exposed to those things? So exposure analysis, other things. Definitely redundant, fault-tolerant hardware, monitors to make sure everything's running, right? You don't get to take off unless the thing, that's why you get stuck, right, is that something says you're not safe to take off, right? And so now you got to go figure out why are we not safe, replace the part, whatever it is. I was talking to somebody, Shankar, this morning about the IndyCar and some cables, right? It turns out connectors are like a major problem on aircraft because they vibrate all the time, right? And the connectors just stop, connecting. They'll go and they'll pull the part out and say, this is working perfectly fine. They put it back in, it's working perfectly fine. The connector was the problem, right? So you got to think about those things. Well, we need to redesign the connectors because if that fails in flight and too many of them fail, right, you got a problem. Okay, so they're very structured operating environments, right? So you're flying at different altitudes, you're on runways, you're all of these things. We have well-trained personnel, pilots, flight attendants, air traffic controllers, all of that stuff. And we have very expensive vehicles, right? We spend a lot of money to build an aircraft, about $1 million a seat. And so I think we can think about this as sort of, here's an example, right, of what it takes to be safe at this level of, 0.07 deaths every billion miles, or 1 failure per billion hours worth of flying. So some of these, I think, are things that we can carry across to things like self-driving cars. So certainly, I think, certification requirements and other things, redundant fault-tolerant hardware. Other ones, probably not so much. It's not a very structured environment, right? Sort of you walk across the street here, right? It's not all that structured, right? We're not going to have trained people all over the place, right? These just people driving around, right? You driving around with self-driving cars. And we can't afford probably $1 million per passenger, right? I mean, that's not, Uber's not going to make any money, right? If the car is costing $4 million, right? And then you got to, sort of get that back through charging things. Okay, so I think this is an area interesting to think about. In addition to these kind of things that are very different, I think one big thing that's different in the aerospace industry is the type of failure. And so I call this sort of functional safety, that's the term of the art, versus operational safety. I don't know if anybody uses that word, but I will. So the idea in functional safety is we want to ensure safety if the components fail. And this is where you use things like fault tree analysis, right? There's a fault, I want to make sure there's a backup, I want to make sure I think about all of the possible things that could lead to this. There's lots of structure around how to do that and make those things work. But that's a little bit different than self-driving cars. In self-driving cars, that's certainly something you want to think about. If I have a flat tire, if one of the computers goes out, right, all that stuff. So you definitely need functional safety. But you also need to think about operational safety. It's a complex environment, right? So this is the corner of 2nd and Howard in San Francisco, sped up. There's a lot going on. And everything could work properly, right? Every algorithm could do what it was supposed to do. Every actuator could do what it's supposed to do. No failures. And you could still have a crash, right? Because a human did something that, maybe you didn't even see. Maybe it was inevitable. There was no way to avoid the crash, right? Because somebody was behind something else. They didn't see you. You didn't see them, and you're going to do it, right? So how do we certify those systems, right? And the number of corner cases is ridiculous, right? Because how many vehicles are you looking at all at the same time, right? So, what's the state space dimension of this thing, right? I mean, there's no way you're going to cover this somehow, right? So this idea of SOTIF, safety of the intended function, right? So SOTIF, the idea is nothing has failed, but how do I tell whether or not, right, I actually designed it in a way that'll still be safe? So I think, just think a little bit about those. So how is this being done now, from my own, kind of consulting work, but also, what I hear and see other people doing, including, again, people here at Berkeley. I think there are lots of things you can do. So first is we're certainly going to do things that are just analytical good design, right? We're going to do, if you're a controls person, we're going to do, sort of stability margins and other things, right? Things like that. So we're going to do things where we say, look, we have very structured ways of talking about these problems and proving things about them and making sure we get robustness. If you're a controls person, this diagram will make sense to you. We're going to think about things like control Lyapunov functions and invariant functions and other things. And again, these are model-based ways of doing things. So, that's a limitation of these, but nonetheless, can be something that we do. Increasingly, and this is work that we've done here with a lot of people on contract-based design, including a previous Ph.D. student, Inigo Inser, who did a postdoc down at Caltech and is studying at Michigan, thinking about how do we decompose the problem and put assumptions and guarantees on the components so that when we put them back together, we know they work, because we know we're going to distribute this design problem. Right, and I remember I said a lot of the failures occur across these layers of abstraction. So how do we think about those things? So all of these things are kind of analytical things we do. That's what I would say, mainly in engineering, right, teach everybody how to do, right? Here's how to design this system, design it to be safe, et cetera. So that's one thing we're going to do. We're certainly going to do that. We're going to do a lot of simulations. Right, and so, Shankar and I were talking about the DARPA Sim to Real program, right? So how do you know whether your simulations, right, are good enough or not? So we're going to use models to simulate these scenarios. The good news is you can run billions of miles worth of models, right? And so, test lots of different things, so you can really get a lot of coverage. But they're model-based. They're only as good as your model. We know all models are wrong. Some models are useful. And so, we know that they're not really going to do things. And the closer it is to reality, the higher fidelity, the less it's true that we can run billions of miles, right? So if I want to run a ray tracing algorithm of everything going on and keep track of the friction on the road surface and everything else on a self-driving car, that's not something I run a billion miles of simulations overnight, right? Probably, right? So, it's not so easy to do. So I think there are interesting research problems associated with this. So how do we think about what models do we use when? If I'm just trying to say, do you obey the traffic rules, wait until somebody else is gone before you go, et cetera, I don't need to know the road friction probably to verify that your logic at that level is doing the right thing. So how do we, in simulation, we get to sample where we want, right? So how do I sample around the boundaries of failure, right? So I really want half of my simulation should fail, right? Because otherwise I'm testing a bunch of stuff that, is too easy. Why should I do that, right? So I think those are interesting things to think about. There's people working on this. So one is some work that came out of here. So Daniel Fremont did some work on something called Scenic. This is a project he continues to work on down at UCSC, where he is a professor now. And so the idea was to come up with these scenarios and then generate scenes, right? Generate variations of the scenario, right? So, kind of do things where you could test things, et cetera. And so we might have some parameter space, right? And we want to kind of spread things around this parameter space and figure out what are the hard cases and the easy cases and do other things. So I think simulation-based, we're certainly going to do that, and we need to do that. Another one is that we're just going to do real-world driving. So this is a video from this morning. 1 Waymo, 2 Waymo, 3 Waymo. Outside the window of my apartment, right? He said, hey, I should have a video that I use for this part of the talk. I literally stood there for about 3 minutes, right? And said, oh, I'll just take a video out the window, right? As soon as I see some autonomous cars come up. And so you'll see they're sitting here, right? The light's red, there's pedestrians crossing, right? This car's now, the light turned green, so this car's gonna come through. It wants to turn left, it's gotta wait, right? This car's coming through. Oh, another autonomous car. There's 4 autonomous cars, right? Literally, I stood there for 5 minutes and I captured a video with 4 autonomous cars. This is the corner of 2nd and Howard, right? 1 block down from the other one. And there's just all these sort of autonomous cars. You can see this car's waiting until it thinks there's an opening, right? Finally sees there's an opening. If you were watching, some people started to come across. And these things, if you've been in downtown San Francisco, you've seen these, right? They're all over the place. So that's one way to do it. So one goes, well, why don't we just test the hell out of them, right? Okay, so Rand did a study. And they said, how many miles would you need to test to show that things are as safe as humans, right? With 95% confidence. So the answer is you need 8.8 billion miles of driving, right? In order to have 95% confidence that you'll have 7 deaths per billion miles, right? So that's what you need. Okay, so 8.8 billion miles. So he's got a test fleet of 1,000 cars. You're gonna drive for each software build, because every time you change things, you gotta recertify. You're gonna drive 8.8 million miles. I don't think so. Right? So that's not going to happen, right? Not that we're not going to do this, we're going to do this too, but it's just not going to be enough, right? And the problem is most of the miles are boring, right? Even the one I just showed you wasn't that exciting, wasn't, sort of tons of stuff going on, but, there's probably 50 things around that you got to keep track of, right? So we can think about, right, okay, we're going to do those things, but how do we, for example, say, well, I didn't have a collision, but I got close to somebody? Can I say, if you're getting close to somebody at this rate, you're going to kill people at this rate, right? Can we make those extrapolations, right? Because that allows, there's a lot more near collisions. We've all been in near collisions, right? Probably like every week you have something where you have to stop pretty quickly because you weren't quite paying attention or whatever, right? So those happen all the time. So how do we kind of take advantage of them? Okay, so regression tests are another, right? So every mile that is run, all of those logs are available, right? And so we can replay those logs. The problem is those logs are on what I saw in the environment, right? And of course, if I change the software stack, I may not do exactly the same thing anymore, right? The whole point of changing it was it did something wrong. So what happens when they deviate, right? So how do we think about that, right? So how do we think about in these regression tests, where do we test? We can test, just the sensors. We can test just the decision-making algorithms. We can spoof things, right? We can insert errors, all of this stuff. Really interesting set of questions. And finally, we can do structured tests, right? So how do we actually go define on a test track something we want to do, right? And the one I usually like to say about this is sort of what we do for people, right, to certify them as drivers. Here's the structured test. You go and you take a written test. Probably takes you about 15 minutes. You fill out a, sort of a multi-choice exam. You turn that in. If you pass that, you get into a car with a driving certifier, instructor, and they basically say for a half hour, okay, drive down this street. Okay, I want you to turn left at this street. Okay, I want you to park in this parking space. Okay, I want you to do this. And after the 30 minutes, right, you are now certified to drive any non-commercial vehicle, any place in the world, in any weather for the rest of your life, right? That's it, right? That's crazy, right? We are not going to do self-driving cars that way, right? But that's what we do, right? That's the structured test that we give. And by the way, if you get an easy instructor or a hard instructor, it's a busy day or not busy day, right? That affects it too. Okay, so I think this is an interesting set of things to think about. And I guess, the first point of this talk is, I hope more of us, right, will work on some of these types of problems. Right? Because it's not the design problem, it's how do we make sure the design actually works. And as we get to things that have a lot of ML and other things in them, right, where we're not quite sure what's going on, but still we can test these things, right? And so we can think about how do I put all of these things together, right? What's the safety case look like for this? How do I get to 1 in a billion? Okay, so that's I think something to think a little bit about, and I hope people will get interested in it. And how do we combine them all, right? What's just the math of combining all these things? And some of it's just statistics, but thinking about where should we test things. Okay, so in my group, we've been doing some work on this one, which I'm not going to talk about today, in terms of, what simulations do you use, how do you use simpler simulations for simple things and more complicated ones for others, and how do you know that's an okay thing to use that model for, right? You can use the simplified model versus the complicated model. So we've done some work there, and I'm happy to tell you more about it. But I'm mainly going to talk just a little bit about this kind of structured test. And the scenario is sort of, what do I replace the 30-minute driving test with, all right, for a self-driving car? It's going to be more than 30 minutes, guaranteed, but it's not going to be 8.8 million miles, right? So I can do something in between those two. And, if you think about it, it's like, okay, maybe I get to define 10 days worth of testing, and maybe in those 10 days you're going to do, 1,000 miles a day, let's say. So maybe I get 10,000 miles worth of testing in. What do you want to do in those 10,000 miles? Because remember, you're looking for something that's happening 1 in a billion. You're driving 10 to the 4th. Right? You're way off. But I can pick what I do, right? So how do we pick what we do? And I think, it's sort of the opposite of a control design problem. I want to make the system robust with respect to something. I want to find conditions that see whether the system is robust to something, right? So it's kind of a complementary question. Okay, so that'll just quickly give a little bit of background, into some of these areas and say some about the kind of the way we've approached this particular problem. So we think about these systems as having continuous dynamics as well as discrete dynamics, and so think of that as a transition system or something like that. We've got cost functions, we want to stay on the road, but we've also got logical kind of constraints that are going on. And so one way to think about all of this is that as we break down what the system looks like, we've got this kind of multi-layer system and multi-layer point of view, and at each level, we've got some model that we're using at that level. It might be ordinary differential equations. It might be transfer functions and linear systems. It might be, sort of finite state automata. And in each of those, we have some sort of specification language that we write down, right? And so we might write down something, again, if you're a control theorist, this line makes sense to you. If you're a robotics planning person, this line makes sense to you. If you're a formal methods person, this line makes sense to you, right? And so making sure that all these lines are consistent is one of the things that we need to do. And in particular, right, I think connecting these things together, right? So we've focused on a little bit this kind of layer at this level. How do I certify, what tests should I run that test out the decision-making logic, but coupled a little bit to what's going on at the trajectory level, because we know that the interface of these things matters, right? And so we've thought some about how to do that. So let me just say a little, I don't need to go into a bunch of detail, but just so that, the symbols aren't completely opaque, let me just say a little about the mathematical language that we use to do this, which is temporal logic. And so there are a number of temporal logic operators. So we think about, depending on your background, if you're in CS, you already know this. If you're in EE, this is the equivalent of transfer functions. Or if you're an applied mathematician, the equivalent of differential equations, right? There's a mathematical language that you use to describe this. So in this mathematical language, we have operators, the eventually operator, the always operator, the next operator. And the idea is that we say some property is eventually true if in some sequence of events, right, at some point A is true. So maybe not A is not true, A is not true, A is not true, and then on the fourth transition of states, not necessarily ticks of time, but transition of states, A becomes true, and then I don't care, right? That would be eventually A is true, right? That statement. Always A true means that A has to be true at every transition of the system, right? And so, on their own, these are perhaps not, that useful, but we can combine them in interesting ways. So for example, just the third bullet there, we can say always eventually P. What does that mean? That means that P needs to be true in the future, and then again in the future, and then again in the future, right? So I need to, kind of continuously do that. Always eventually check your rearview mirror. Always eventually be in your lane, right? These are the types of properties that you might want to have true. You can also flip them around and say eventually always P, right? What does that mean? Eventually P will be true and stay true, right? And so if you're landing an airplane, you say eventually I want to be within 1 centimeter of the middle of Illinois. I want to stay within 1 centimeter of the middle of Illinois, right? You could say that. So this language allows us to write down formulas for what can be done, and we can expand this to include time and various other things. But you can think about this in a kind of simple way. I might have a stoplight. This is a European stoplight. I was just in Europe. So in Europe, as you may remember, when the light's red before it goes green, right, the yellow light and the red light turn on at the same time, then it goes green, right, and then the yellow light and the red light, right? And so you can write down what are the temporal logic properties that you might want to be true. So for example, you'd like that lights always eventually turn green. We all wonder about this sometimes when we're in parts of the world. Come on, I back up over the sensor, whatever's going on. We'd like maybe that it's always true that if it's green, then it's not not red at the next step. So this little circle means next. So it doesn't go just from green to red, right? That wouldn't be fair. And this is a more complicated one that says, essentially if it's red, then it goes green, but not until it's turned yellow, right? And again, this would be the European version, right, of all of this, right? So that the yellow turns on to let you know. So we can write down these properties. And now with this mathematical language, we can start to do things. So on the design side, not the certification side, but the design side, one of the things we can do is we can synthesize our controllers, right? So you can say, look, I've got a process. It's a discrete finite transition system. Do I go? Do I stop? Do I turn left? Do I stop? I've got some environment. All of the other cars around me, they can do things. And I want to synthesize a controller, that thing C, right, that says, in some model of what the environment can do and some model of what I can do, I will always satisfy some set of properties. And so here, for example, is a set of properties. This actually came from the electric power system work that we did with Edward Lee and Alberto Sangiovanni-Vintelli, talking about what we wanted these to do. And so we can synthesize that controller, but the problem is it's not scalable. Doubly exponentially complex in the size of the spec. So you got 5 specs, that's 2 to the 2 to the 5th, 2 to the 32nd, not too bad, right? You got 10 specs, that's 2 to the 1000th, more than the age of the universe in nanoseconds, whatever, right? You're done, right? So this doesn't work, right? So nobody does this. But it turns out that there's a sort of a subclass of specifications called GR1 for general reactivity. And what happens in GR1 is that we essentially break the symmetry. So we assume that the environment makes a decision, then the controller sees that decision, makes its decision, and then they both implement that decision, right? And then the process dynamics flow, and then we do it again. You say, well, that's not fair, right? Why does that happen? But if you're running fast enough, it's not a bad approximation. If every millisecond I look to see what the environment's doing, it's not going to change that much in a millisecond. If it does, I'll catch it 1 millisecond later, right? So it's not maybe a terrible assumption. So if you make that assumption, and in addition, you assume a certain class of specifications. So this is what's called a general reactivity spec. I won't read it here in detail, but it basically says, if the environment does stuff reasonable, then I want the system to do things that are reasonable. Be safe, right? Sort of not block me forever, things like that. Then it turns out that this reduces the complexity from doubly exponential to cubic in the number of states required. That's huge, right? This is like telling you that this is essentially a convex program. Actually, it's like telling you it's a linear program, right? I mean, it's like all of a sudden I can solve things at a certain scale that I couldn't before. Now, there's a little bit of lying in here in terms of number of states versus number of specifications, right? But that's okay. It's actually a pretty good thing. The number of states required to do these things is not bad. So GR1 synthesis is an example. And so these general reactivity formulas, and they have this assumed guarantee. Under some assumptions about the environment, I'm going to guarantee something's true. Right? Under some assumptions about what the upper layer is going to do, I'm going to guarantee some things at the lower layer, right? So you can play all these things through this. Okay, so I'll just give you a really simple example to kind of show you how this goes in terms of the synthesis and sort of how you can think about it. So this is a game that Amir Punelli, now dead, passed away a couple of years ago, did where, very simple, kind of academic example. I've got a runner. The runner's goal is to get to the goal. So it's trying to get here, so eventually G. It can go up or down. I've got a blocker. The blocker can be in one of 3 positions, middle, top, or bottom. Right? And the idea is that the runner should get to the goal without being blocked. Now, I need some assumptions. For example, if the blocker sits in the middle all the time, right, and it moves at the same time I do, and I don't know which one, remember this will break that symmetry, right, then I'm kind of screwed, right, because essentially it sees which way I go and it goes that way, right? So we'll put some assumptions in that basically say the blocker can't stay here forever, right, and we know which way it's going to go. So the blocker eventually has to move. As soon as the blocker moves down, I go up. As soon as the blocker moves up, I go down, right? I mean, it's obvious how to solve this. But how would you do this if wasn't obvious? So the way that you do that in a GR1 synthesis problem is you basically enumerate all the states. You don't really enumerate all the states. You do this in symbolic representations and other things. And then you say, okay, great. Here's where I want to, so here are all the transitions. So, the system can move, the environment can move. The red is the environment, the blue is the system. And here's where I want to get, right? This winning state down here. I have reached the goal. And here's where I want to avoid, right? These losing states where we're both at the same position. And then what we're going to do is we're going to say, great, let's suppose that I start at the winning state and I ask the question, what are the set of states from which, if the environment takes an action, I can take a counteraction that leads me to that winning state. And if you do that, right, you get to add in a couple of states. Because this is sort of trivial, there's only one action I could take anyway, right, but I end up in that winning state. And now that's a new winning set, right? And so now I can say, great, what are the set of states from which, if the environment were to do that, I could take a step that would get me back into that set, right? And I do that. And once I hit the initial state, I know I can win, right? I can back out a strategy from this, right? Because I can basically say, at any action that the environment takes, I know there's one of the 2 actions I can take that pulls me back into this set. And once I'm here, whatever the environment does, I can get down here. So I know I'm going to win, So this lets me get a strategy. So that's the basic idea behind GR1 synthesis. That's it. Okay? And so from this, I can both check to see that the problem is solvable, and I can give you a solution to the problem. I can define my controller as a finite transition system. Okay, so how do we apply some of these ideas in the context of certification of testing, right? This is for synthesizing a controller, and that's work that we did a long time ago. So now we kind of come back to this problem of, this is the environment that we want to deal with. And so how do we perform this operational test, right? I'm going to give you 10 days, right? Maybe you can drive 1,000 miles a day. What should you do? And this is hard, right? Because the systems are complicated and there's lots of possibilities. This is from the DARPA Grand Challenge. This is the Caltech team. This is now an intersection where DARPA set up a test. And they put 3 cars at this intersection, and they had one of them go and then another one go, and they decided is it going to turn left or straight, right? And then we get to go, right? And so they came up with this test. They said, this is a good test to somehow convince us, right? By the way, the DARPA Grand Challenge was about 5 days worth of testing, and we maybe drove 10 miles total, right? Now it was a controlled environment for the final things, et cetera, right? Here we come up on another one. Now they've set up a different test, right? Now in this one, a car's in front of us, right? We've got to wait until it goes. Then we come up here, but that car was here first. It has the right of way. It's to our right, right? And so now once it goes, now I can go. Right? So they came up with these tests, but how did they come up with these tests, right? How do we think about, is that a hard test? Is that an easy test, right? How would we say all of them? So what we've thought about is, for example, can we synthesize that test, right? Can I give you, here's the specification, turn that into a test. So instead of manually creating test suites, how do we automatically create test suites? We want to think about dynamics, uncertainty, and reactivity, right? There are dynamics of the system, right? This is the kind of coupling of layers. And we want to take advantage of the structure, right? This can be specified as a GR1 problem, right? So I know there's these nested winning sets and other things that are playing around, right, underneath what's going on. Actually, I should, in the usual way, take advantage of any mathematical structure I can. And so we've thought about, how do we, with this mathematical structure, generate, desired properties for the test sequences. Turns out it's not an opposite GR1 synthesis problem, that is, do GR1 synthesis for the environment, because the environment's playing a weird role, right? It's trying to make sure you can still succeed, but at the same time not make it too easy. So it's slightly different, so you have to change things around a little bit. Okay, so of course you also want to make use of all of the other stuff, right? This is one column, right, in that whole thing. Remember that, I'm not going to be able to, test everything, but I've got millions of miles of driving, billions of miles of simulation, right? Analytic guarantees, right? All of those things as well. Log tests, all that. Okay, so just to kind of say the little bit about what we've done here. So we're thinking about these multi-layer systems. We're going to focus on this top layer. We have a system specification, which we take as there's a safety condition. Always certain things are true. There's a liveness condition, or in this case, a reachability condition. Eventually, something is true. We have a test specification. So the way we've structured is you need to tell me something about what you want to see. I want to see an unprotected left-hand turn. I want to see you change lanes, right? But I want a hard change of lanes. I want a hard unprotected left turn, maybe. And so we can do this, and these are all happening in discrete spaces, and so we can form essentially a compositional state transition diagram that codes both the system spec and the test spec. And we can put this together with the dynamics of the system and eventually get a product graph. The way to think about this graph is that as the system goes through its simulation, you're traversing paths on this graph. And the idea is that I'm going to start someplace at the beginning of the test. I want to get to some state. That's the set of states in which you've actually, let's say, made it to the goal or whatever it is, right? You've satisfied, made the unprotected left-hand turn. But the test spec says I want to see you do certain things. So I want you to only get there by going through. I want to see a certain thing, and that's a certain set of states that sort of let me see that. And now we can formulate this essentially as a max flow problem, right? Give me, right, cut edges, that is, put environmental constraints in a way that doesn't let me do anything, but lets me do as many things as possible, but all of the things that I can do will always show my test spec was satisfied. I'll go through that intermediate node. So this turns out to be a mixed integer linear program, which we've got pretty good algorithms to solve, and we can do in pretty good ways. All right, so that's an idea about how we might do all of this stuff. Okay, so we then take these cuts and we have to project them back into the physical space. And so I'll just show you this in 2 examples. One is an example in which we said, okay, well, I've got a walking robot, and I would like to see this walking robot. I want to make sure that it can lie down, that it can stand up, and that it can jump. And the way that we're going to do this is we're going to have 3 doors, and the key for the 3 doors that you have to get can either be on the ground, right, at the level of the height of the sort of robot, so it just has to stand up, or up at the top, so you have to jump. And now my test specification is I would like you to design a test. You've got to figure out where do I put the keys and which doors am I going to allow you to open, such that I see you lie, stand, and jump. So you need to say that. Now, I don't know which door you're going to go to, right? I don't know what the controller is, right? I just know that you've been told you need to get to the other side. There's a beaver here. That's the Caltech mascot. We got to rescue the beaver. You know how it goes, right? So we know that at least one of these doors will be open. That's an environmental spec. We want to make sure that we design the test so we do that. So you can actually do that, and so we synthesized a test that essentially does that. So here what you're going to see is the actual robot running around. This is going to tell you sort of where the key is. It's hard to see it in this video. And then the robot has to get the key and try and open the door, and the door may or may not open, right? And then we don't know which door it's going to go to first, and we don't know necessarily that it's going to jump or do the right thing, right? So once we see what it does, then it'll go and it'll explore the next door, which is down on the other end, and we'll sort of see what it does. And so as we go through this, right, it sort of comes up. The doors are open. We didn't actually close them. It comes up. One of these lights turns on. I think this is the middle one. It stands. It gets the key. It tries to open it. Nope, sorry, it's locked, right? That's not the right key. It doesn't do it. Okay, great. I'm going to go to a different door. So it goes down to this other door on the other side. As it gets down to this other door on the other side, we know now that it has stood, right? So now we can control those lights. So we say, great, right? Now we're going to put it up at the top. And so we're going to make you jump. So it jumps. Doesn't really jump that high. But anyway, you get the idea. And then we say, nope, sorry, that one's locked. Because why? Well, we haven't seen it lie yet, right? So we know we need to do that. So now it's going to come back to the other side and lie down. So the point of this is that, that you could probably come up with this test. It's like the DARPA Grand Challenge people, right? We're going to put this number of cars there, and we're going to do this, et cetera. But this was all synthesized from a test spec, right? No manual intervention, right? We told it, I want to see you execute these two things. I need to make sure you can eventually get there. So at least one of the doors needs to be open, right? And it's a reactive test, right? As I see you come up, I say, nope, sorry, that one's not going to open. Maybe, on a different test, it might have gone to a different door first, different pattern. Okay, so now it's rescued the beaver. A little bit of magic will happen here as the beaver gets rescued. Okay, so that's the idea. Here's another example where we said, okay, I want you to start at this source. I want you to get to this target, but I want you to go through both I1 and I2. And of course, if I do nothing, right, you could go, there are lots of ways you could go that would avoid both I1 and I2. You could imagine, say, well, I'll put some roadblocks here. Right? If I put roadblocks here, this will make it so that you either have to go through I1 or through I2. You can't avoid both of them if you think about the paths. But once you've gone through one, I need to change where the obstacles are. So for example, if you visit I1 first, I need to block off so that you don't go straight to the target. So now you have to go back around through I2. And this one we said, can we actually get that pattern not by having obstacles that sort of pop up, but actually having a robot that implements that pattern? And so we did that by saying, can we have this middle robot implement that test strategy? So the robot, we don't know where it's going to go. Oh, it went through I2. I don't want it to go through the target, so now I say I better block it off. So we go block it off, right? It comes up, we say, nope, sorry, this is blocked, right? It goes back the other way, right? Now, we know, right, that it could go through that middle, so we're going to block off that middle, right? Because we don't want it to do that. So we're going to come and stand in the middle. The robot, right, doesn't have very good vision, right? So it goes up and says, oh, I see, this one's blocked too, right? So now I'll go back around, right, and I'll go through that bottom spot. So again, this was synthesized, where now we synthesize not a set of obstacles, right, but a reactive strategy. We told the other car how to drive in a way that tested the thing that we wanted to test. So that's the kind of work that we've been doing. Okay, so let me stop there. And so, I think coming back to this question, right, how do we make sure autonomous systems are safe enough, 1 in a billion? Brute force isn't going to be enough. Right? So again, we're not going to get this kind of 8.8 billion miles per release. That's not going to make any sense. Simulations are only as good as the models. Not that we shouldn't do that, but you're never going to get, I think, everything that you need. So I think that we need to do things that make use of a combination of methods. I've shown you one here. We've done some work on different levels of modeling and other things, and as I mentioned, didn't have time to talk about it here. But I do think that it's something that is worth thinking about. And again, more people working on this, because these things are out there, right? I mean, the picture from this morning at whatever it was, probably about 8:15 a.m., right, was really what's happening in the city of San Francisco right now, right? 4 or 5 autonomous cars driving around. I went down to get on the BART train, and an autonomous car came up, right? And I'm sitting there going, okay, I know what's going on under the hood. I'm not sure I trust them. They haven't had too many accidents, but from the papers, right? 1 in a billion. I don't want to be the one, right? Or the point, whatever it is, 7, right? One of the 7. Okay, so I think there are some history and lessons we can take from aerospace. One is, and this has been hard, it really needs an industry-wide approach. It's really hard to get these autonomous car companies to talk to each other. The people that were, sort of Claire will remember, and Chaka will remember, when we were running the vehicle program, right? We'd get all autonomous car companies and say, what are the problems you have? And like nobody would say anything, right? They just would not talk, right? It's like, come on, So, we're not saying it because we don't want to say where our weak points are, right? So how do we get by that? I mean, it's a social problem, but we got to do it. There's likely to be lots of industry. What we saw what we saw in aerospace was that it was not regulated, then it was over-regulated, right? Then it was under-regulated, right? Because if you over-regulate it, you basically shut down your industry, right? And you want to be the ones that are selling autonomous cars to the rest of the world, right? So then the car companies say, hey, we're not able to, sort of do testing or whatever, right? So then you under-regulate it, and then, right, people crash, and then you go back and forth. So we'll see that happen here too. Right now we're in the under-regulation. There's essentially very little regulation going on, certainly at the national level. And it does feel a little bit like the Wild West in terms of what's out there. And if these are going to be deployed at the 1% level or the 10% level or the 50% level, I think as a community of engineers, we're going to have to figure this out. So with that, I will stop there, and thank you for your time and attention.
Maybe we have time for one or two questions. Christian.
I have a question. So when I think of these cars, if you have your driver's license for 1 day, this will not happen to you. But if you have been driving for, let's say, more than 10 years and less than 100, like me, then you probably had many times in your life a situation where somebody else made a mistake, and if you had reacted the right way, there would be a crash.
Right.
If you're driving in Berkeley, you probably in the last year had a situation where if you had not stopped, even though you didn't have to stop, there would be a student on a scooter be killed.
Yep.
Okay. How do you deal with that for your class?
Yeah.
Probably for the Berkeley students, okay, we are intelligent enough to train your autonomous car. There will be the students who cross in front of you, even though they would be killed if you didn't react, so you teach the car to react. But there are probably other situations you and I got into where we reacted, which nobody would have predicted.
Yeah, so one of the things you find the autonomous car companies are doing is they're trying to work hard to define blame, right? Whose fault was it, right? Because, of course, that matters, right? I think, definition of that would be, I think that what we ought to strive for is to say, look, if a collision was inevitable, right, then we should worry about blame. If you jump out in front of me and I'm driving under the speed limit and you jump out 5 meters in front of me and I can't stop in that physical distance, and people, recognize self-driving cars are going to kill people. That's just going to happen, right? So it's hopefully at a much lower rate, right? So I think we have to do it that way. But I would say that my expectation would be that, assuming no failures, if it was possible to stop, right, with the information that I had available, that self-driving car would avoid the collision, which is what I think you did, right, when you sort of said, holy crap, the scooter came out in front, I'm going to jam the brakes on, right, and make sure that I don't run into them. Even though they broke the law, you actually probably could not have kept driving and not gotten thrown in jail, right? I mean, because I think that's what the law would say too. Well, why didn't you stop? Well, they were breaking the law. I don't think that works, right? So I think it's going to be the same sort of standard. But the car companies have to get you, and they are, I mean, they're ready for deaths to happen, right? They're ready for people to get killed, meaning that's going to happen. And part of the argument's got to be yes, but, right? Think how many humans would have died, right, with that same amount of driving that we've done and other things, right? So I think that's where we got to get. And again, the aircraft industry is kind of that way.
Kameshwar and then Edward.
So, first I'd say that if you truly want to test autonomous vehicles, if they can drive in Bombay,
Yeah.
they can drive in Palo Alto.
I agree. I have some videos, right? Yeah, indeed, right? From Mumbai and other places, and you're right? I mean, but how do you say that formally, right?
My question is, what about the space flight program? How did they put safety into?
Yeah, I'm not a huge expert, so I'm speculating a little bit, but I do think it was very much that sort of functional safety point of view, right? If something fails, what's the backup system that does something, right? We just had the astronauts got left on the space station. Our backup was we're going to send a SpaceX thing up there. It was at a high level, right? But that's sort of what you do. Why? Because we couldn't convince ourselves, right, that the Starliner or whatever the Boeing one is called, right, was going to be able to, right, sort of come down. It did, right? It was perfectly safe when it came down. And the Boeing engineers would say that, right? But we had to have a level of surety there, right? That was that way. So I think in the space program, I think what's different about self-driving cars is the accidents, my guess is, most of the accidents are going to happen not because something failed, but because the environment was something we hadn't seen, right? If you know a little bit about, the incident that happened with Cruise, right, where, two people at an intersection, one car goes forward, hits a pedestrian, knocks it into the way of the Cruise car, speeds off and keeps going, and the Cruise car runs into it. Holy cow, like who would ever simulate that situation, right? Nobody. But at the same time, right, the Cruise car did something that I think, certainly the public said, wait a minute, right? After you stopped and this car was, this person was under you, pulled to the side and dragged them, right? That's crazy, right? So I think figuring that out is going to be hard, but I think that's different than the space program, where what you're really worried about is not that, green spacemen are going to come out and do something you hadn't inspected or expected, but that a thruster is going to fail, right? Or that we don't know the thruster. So I think that's the way I would probably answer that question. Space industry, I think, does this in the same way the aerospace industry does this. One difference is the aerospace industry has tons of data. You want to know how often this component fails? We know how often this component fails because we're flying that component thousands of hours, right, all the time, right, millions of hours, right, over the course of a year. That we don't have as much for the space program. And you do see, catastrophic failures, Mars landers that, do the wrong thing, et cetera.
So it's very refreshing to hear talking, no mention of large language models.
It was in there. There was an ML that showed up, and that should have been LLM, right? Yeah.
The reality is that with those systems, they don't look a lot like those autonomy models, and they're quite a bit harder to model technologically. So I was just wondering what your opinion is about how that changes the safety.
Yeah, I think it's really going to change things. Now, there's kind of 5 buckets that we look at, right? And so I think one of the places it's going to change things is that we may not be able to rely on that analytical bucket, right, sort of safe by design bucket, because we just don't know, right? And so I think we're going to have to rely more on some of those other buckets, right? Sort of simulation, right? Sort of hard testing, right? We're going to, and people are doing this, right? I mean, coming up with things that spoof the algorithm and try and break the LLM and all of those things. So I think we're going to just have to build that in, right? So one of the things that we've sort of said is, in the way we formulated the problem, I'm allowed to know what the spec is. We've simplified a little bit by saying the test engineer gives me something they would like to see, right, the test spec. And then I'm going to assume no other knowledge about what the system does, except its physics, right? So I know something about, it can't jump to the other side of the road immediately, right? But we don't make any assumptions about what's underneath the hood, right, what's going on in there. And so now, maybe that means we won't be able to solve it, right, as we get to really bigger scale problems, et cetera. Maybe without that structure, we just can't solve the problem. But at least without that structure, I don't care whether you've got a LLM model, right, or an LQR controller running on the inside, right? It's the same to me. Here's the system spec. Here's what I want to test. Let me come up with a hard environment for that test. That's the part of the problem we want to solve. But you're right, right? The problem's going to be that the failures are going to be rare, right? And so, you're going to have to test all those, or see all of those corner cases, right? And again, at the level of 7 in the United States per year, you're getting some statistics, but you're not going to fine tune a model, right, on 7. Right? So I agree, it's hard.
All right. Let's thank Richard again for a great talk.
Thanks.